In part 3 of chapter 3, we are going to start talking about the acid-base properties of amino acids. And so what you're going to see here is that we are going to focus on the individual functional groups of amino acids and really how their acid dissociation constants impact the ability of, say, the alpha carboxylic acid or the alpha amino group of an amino acid, how those groups impact the overall behavior of the amino acid. The amino and carboxyl groups of amino acids, along with the ionizable R groups of some amino acids, function as weak acids and bases. When an amino acid lacking an ionizable R group is dissolved in water at neutral pH, it exists in solution as a dipolar ion. We also refer to this as a Zwitter ion. Zwitter ions can act as either an acid or a base. So if we look at the slide in front of you, I'm showing you an example where we are looking at an amino acid that lacks an ionizable R group. So this could be glycine, alanine, leucine, isoleucine. It could be, say, methionine. Really what we're talking about is something where your R group has no pKa that is defined for it. It does not have an ionizable R group. So in those cases, our ionization properties really are dependent only on the alpha amino group and the alpha carboxylic acid. This is a typical representation of what you can expect going forward. So when we look at these things, when we look at amino acids and we start talking about ionization properties, usually what we're going to do is draw out the fully protonated form, which is what you see here on the far left-hand side. Here your carboxylic acid is fully protonated. Your primary amine is also fully protonated. And what I want you to really start thinking about here, what I want you to understand, is that the fully protonated form of these two functional groups gives a different charge. What I mean by that here is that when I fully protonate a carboxylic acid, I have a neutral functional group. Only upon dissociation of the proton from the carboxylic acid to give the carboxylate, which is what you see right here. So you go from carboxylic acid, Cu, to a little bit less Cu, your carboxylate. That was a really lame joke, forgive me for that. But here you go from a neutral charge to a negative charge. In contrast, for the primary amine, when fully protonated, you have a positive charge. And when you lose that proton, you go from NH3 to NH2. You go from positive charge to neutral charge. So please do not fall into the group of students that wants to apply one-size-fits-all rule here. Sometimes you'll find students that say, okay, when fully protonated, regardless of functional group, I have a +1 charge. And when I lose a proton, I go to a neutral charge. There is not a one-size-fits-all explanation here. You have to look at the functional group in question. So here, this is a pretty neutral, pretty normal workflow here, where we start with a fully protonated amino acid. Remember here, this is an amino acid that lacks an ionizable R group. So in doing this, in the fully protonated state, we have a +1 overall net charge. If you look around, there's only one thing that has a positive charge. That's the primary amine. Now, as I increase the pH, I'm going to start promoting dissociation of protons. Remember here, we are looking at pH relative to pKa. So of these two functional groups, if you were paying attention in the last recorded lecture in part 2, I showed you a big giant table of amino acids, their names, symbols, pKa's, and if you recall, I summarized the alpha amino and alpha carboxylic acid pKa's. I told you that the alpha carboxylic acid pKa's tend to be around a value of 2, and the alpha amino group pKa's tend to be between 9 and 10, so on average 9.5. So what that means is if I'm in the fully protonated state down here, I'm starting out, let's just assume, at a pH below all of your pKa's. So if this functional group has a pKa of 2. I'm just going to start just arbitrarily and say I'm at a pH of 0 or 1. Okay, then I start titrating the pH upward. I titrate it such that it is higher than my first pKa. So 9.5 for the amino group, 2-ish for the carboxylic acid. So really what I'm doing is I'm raising the pH in this step above 2. When I do that, I promote dissociation of this acidic proton to give the carboxylate, and now I have a neutral species. Okay, the +1 charge cancels the -1 charge, and I have a net charge of 0. Cool. Now if I keep on increasing my pH, now to above the pKa of the alpha amino group, so to a pH above 9.5, I can promote dissociation of one of these acidic protons from the primary amine to give the NH2. So let's say I raise the pH to pH 11. Now I encourage dissociation of that proton, but now my overall net charge changes once again. So now the primary amine has a net 0 charge. My carboxylate is still negatively charged, so I have an overall charge of -1. So what you're going to see going forward is this logic play out multiple times in multiple ways. What I want you to start to become comfortable with is writing out the various ionization states for these amino acids. And I've given you the simplest case here where you don't have to account for an ionizable R group. Building on the concept of the Zwitter ion, we can now transition to talk about the isoelectric point. First, conceptually, all this is the pH at which a molecule carries no net electrical charge. Okay, from the previous slide, you should remember that for an amino acid that lacks an ionizable R group, you're going to have 3 possible species that differ with regards to electrical charge. There's a species that had a +1 charge, a species that had a net 0 electrical charge, and then a species that had a net negative electrical charge. The pH that maximally populates that species that is neutral, that pH is your isoelectric point. So mathematically, we calculate isoelectric point as the average of 2 pKa's. Recall that the pKa is just simply the measure of the tendency of a functional group to give up a proton. So here, what we're doing is we are focusing on the functional groups that are going to lead to the net neutral species. This is always going to be quantified as the average of 2 pKa's. So do not overcomplicate the math here. The thing that is going to complicate this, and you'll see going forward how this plays out, is whether or not you have an ionizable R group. If you do not have an ionizable R group, then the Pi is just simply the average of the pKa's corresponding to your alpha amino and your alpha carboxylic acid functional groups. The amino acid that does not have an ionizable R group, this is just a dipolar amino acid, has 2 ionizable functional groups. So if you take the average of the pKa's for those 2 groups, you are simply finding the midpoint in between them, and this is the pH at which you're going to get no net electrical charge. Now, if you do have an ionizable R group, the logic here has to be a little bit more justified. You have to identify which functional groups, which functional groups, when protonated or deprotonated, which combination of functional groups is going to give you the 0 net electrical charge species. So you'll see in a moment how you would go about identifying which functional groups to incorporate here, but I really want to hammer in the idea that the isoelectric point first is just simply the pH at which your molecule carries no net charge. So this is the pH at which you are going to lead to maximum formation of the 0 neutral species, the species that has a 0 net charge. And quantitatively, this is simply the average of 2 pKa values. That's all it is. So on an exam. I don't want to see you sitting down and trying to take the average of all of your functional groups. I have had students do this. That is not correct. What is correct is just simply the average of 2 pKa values, not the overall average pKa value. So don't overcomplicate this. Let's look at the example of glycine. First, remember that glycine has an R group that is a proton. So it is a truly dipolar amino acid. It has an R group that is not ionizable. The only ionizable groups here are the alpha amino group and the alpha carboxylic acid. So before we look at the quantitative, the actual calculation of the isoelectric point, we're going to look at the data. Here you have a plot of pH versus OH equivalents. You can think about this just like an acid-base titration that you've done in general chemistry or analytical chemistry. So here you have the first, remember you have your 2 ionizable groups of glycine, and you're going to titrate them with a strong base like sodium hydroxide or KOH. Some strong base, and you are effectively titrating in OH equivalents. So here you have basically volume of titrant or concentration of base, however you want to view this. And as you titrate in more and more base, your pH goes up. Now when I look at the actual data, what I see is basically 2 different titrations. There are 2 different stages here. So in this first stage, as well as in the second stage, each of them corresponds to the deprotonation of a single group on glycine, hence the reason that you have 2 stages. You have 2 functional groups that are ionizable, and you're titrating in base, therefore raising the pH. And so essentially what you have are 2 individual titration curves that resemble in shape the titration curves of a monoprotic acid like acetic acid. And for that reason, you can do the identical analysis that you would do for a monoprotic acid. At the midpoint of each stage, you have equal molar concentrations of acid and conjugate base. So remember, when we looked at buffers, we always had a midpoint. You had an effective buffering range, and that's actually what is defined by this blue box here and up here. And the midpoint corresponded to the condition wherein you had equivalent amounts of acid and conjugate base. So for this first stage, my midpoint equal to pH, or actually it's written here as pK1 equals 2.34, but because I know at the midpoint I have pH equals pKa, I know that the pH here is also 2.34. Okay, so that would be the first stage. If you hop to the second stage, you can do the same sort of analysis. And so what I want you to see here is that first, the midpoint of these 2 separate stages corresponds to the condition where your acid concentration equals your conjugate base. So from the Henderson-Hasselbalch equation, what this absolutely requires is that my pH equals my pKa. So under these conditions, I have 50% deprotonated, 50% protonated. So let me step back and sort of remind you here. The fact that I see 2 stages first tells me I have 2 ionizable groups, and now because I can quantify the pKa based on the midpoint of each of these transitions, I also know what the pKa is for each of those 2 ionizable groups. If you want to view this structurally, imagine I start at very low pH. I start with my fully protonated glycine species. I have my alpha carboxylic acid that is protonated, alpha amino group protonated. I have my +1 species. Okay, so that would be the dominant form down here. But now, I'm raising the pH by doing this titration, right? So I start to promote transition to this species. The only difference here is that my carboxylic acid has deprotonated to the carboxylate. Okay, now remember, the functional group that is undergoing the deprotonation, this is dictated by pKa. If I know just back of envelope rough numbers that the pKa for my alpha amino group is about 9.5 and the pKa for my alpha carboxylic acid is about 2, then as I look at the data, I can guess, I can sort of make educated guesses about which of these stages corresponds to which functional group. The first one, because this occurs at a pH of 2.34, I can reasonably say, oh yeah, that's probably my alpha carboxylic acid. Because this one, the second stage, occurs at 9.6, a pH of 9.6, I can, if I know anything about the pKa values of an alpha amino acid, I can reasonably predict that's probably my alpha amino group. Cool, cool. So hopping back over here to focus on this transition for a moment, I know that when my pH equals my pKa, I have 50% acid, which is what is the starting species here, and 50% conjugate base. Okay, now I hope you're paying attention because I'm about to start dropping in a little bit more nuance. When my pH equals my pKa, when I am at a pH of 2.34 for glycine, my overall net electrical charge for that solution is the average of the charges on these two species. So this species, the fully protonated state, has a +1 charge. My carboxylic acid has a 0 charge. My alpha amino group has a +1 charge. And for the deprotonated species that results, I have a net 0 charge. So +1, -1, 0. Now, if my pH is equal to 2.34, if I am at this very condition, the overall electrical charge for my solution is the average of 1 and 0. So for those of you that have forgotten how to do that math, the average of 1 and 0 is 0.5. So when my pH equals 2.34, my overall net electrical charge is 0.5. Okay? This should make sense based on your knowledge of the Henderson-Hasselbalch equation. Remember, when pH equals pKa, I have 50% of this, 50% of that. Acid, conjugate base. Now if we hop over to the second stage, the same exact treatment can be applied. If I start down here, I assume that I have mostly this species. So here I have a net 0 electrical charge. I have a neutral species here. And I increase the pH above the midpoint. Remember, the midpoint here is my pKa2, the pKa for my alpha amino group. So as I deprotonate this to the NH2 species, I go from a net neutral species to a net negatively charged species. So 0, -1. When the pH equals 9.6, I have 50% what is effectively acid here and 50% conjugate base shown here. Okay, so my net electrical charge at pH equals 9.6 is the average of 0 and -1. Okay, so there, the average of 0 and -1 is -0.5. Okay, now we are converging here on to our conditions of pH equaling Pi. What I want you to see here is that at my Pi, my overall net charge is going to be 0. This is the condition that overwhelmingly populates my neutral species, my species that has no net electrical charge. Okay, so mathematically, this is the average of these two pKa's. The average of the two pKa's gives me the midpoint, the mathematical midpoint that occurs in between. So if at pH 2.34, my overall net electrical charge for my solution is positive 0.5, and at pH equals 9.6, my overall electrical charge for my solution is minus 0.5. The average gives me the midpoint in between those two numbers, and also gives me a condition where my net charge is 0 overwhelmingly, because I have found the midpoint between, basically I have found the condition that is most likely to give me the solution that has a 0, a neutral electrical charge. So in this case, my isoelectric point is defined as the average of 2.34 and 9.6, which gives me a value of 5.97, which is my midpoint here. Okay, so that was a lot. That was a lot to throw at you. And I'm going to work out additional examples to really hammer in what we have done here. But what I want to highlight to you first is that all of the problems like this for isoelectric point are going to involve you drawing out all of the different ionization states for a given amino acid. Being able to draw the amino acid structure is going to be essential to doing this. So you're going to need to know what the amino acids look like, or at least be able to reasonably access them in a quick period of time, and have some idea of what the pKa's are for your amino acids. Okay, so before I move on, what you're going to see is that isoelectric point is going to be very important for making predictions about a molecule's behavior in solution. When your amino acid, or rather your protein's pI equals the pH of the solution in which it lives, that is going to be a case where you have, for proteins at least, the lowest solubility. For amino acids, this is a little bit different because you do have two different charges to form hydrogen bonds with an aid in solubility. But for the amino acid, you can at least make predictions about the overall charge. So at any pH that is below your pI, so here's your pI, at pHs below that pI, you are going to have an overall positive charge for your amino acid. This should make perfect sense. If at my pI I have a net 0 overall electrical charge, and let's say when my pH equals 2.34, based on the logic that we've already laid out, I have an overall charge of 0.5, then really anything between 0.5 and 0, which occurs at my pI, is still a positive charge. So when the pH is below my pI, my amino acid has a net positive charge, and at any pH above my pI, my amino acid has a net negative charge. Remember, pI is where you have conditions of neutrality. You have 0 electrical charge here. At your next pKa, you are forming a negatively charged species, and so basically you're going from 0 to anything above that being negative overall charge. Anything below that, positive overall charge. So if you just want to remember this, at any pH below pI, your amino acid has a net positive charge. Remember here, we're talking about glycine, or amino acids that have no ionizable R group. So this is a general rule that applies to those. At any pH above pI, your amino acid has a net negative charge. Okay, I just gave you the pKa information for glycine. I told you that the pKa of the two ionizable groups are 2.34 for the alpha carboxylic acid and 9.6 for the alpha amino group. One thing to point out here is that the carboxyl group of glycine is over 100 times more acidic, that is 100 times more readily ionized than the carboxyl group of acetic acid. So if we look at the figure up here, you'll see you have a pKa of 2.34 for the alpha carboxylic acid group of glycine, and the corresponding pKa in acetic acid is 4.8. It's actually 4.76, but that rounds to 4.8. Now, acetic acid is commonly used more as the reference, the benchmark here. Acetic acid represents more of like just an average carboxylic acid. It is attached to an otherwise unsubstituted aliphatic hydrocarbon. It's actually a methyl group, but you can treat this as, a hydrocarbon. And so here, this pKa is more of the representative pKa that you would find for the carboxylic acid without any sort of additional influence by adjacent atoms due to, say, electron withdrawing or things like that. Okay, so glycine. This carboxylic acid is more acidic than the corresponding carboxylic acid in acetic acid. Now, why is that? Well, if you remember that you are in constant equilibrium between protonated and deprotonated, this should make sense. Our product here is actually stabilized. The product here being the Zwitter ionic form is actually stabilized due to the opposite charges. So the opposite charges on this resulting Zwitter ion are stabilizing. The positive charge, the negative charge, they electrostatically stabilize one another. There's an attractive force. So you have product stabilization that actually shifts the equilibrium to the right here. Okay, so that's the explanation for the perturbed, or rather depressed, pKa for the alpha carboxylic acid. The product form here, the Zwitter ion, is more stable. Therefore, the favored protonation state for the carboxylic acid is the deprotonated carboxylate that stabilizes this interaction. Now, what about the alpha amino group? There's a perturbation in pKa there as well. And if you look at the corresponding pKa for your alpha amino group, it's 9.6. If you look at methylamine, again, methylamine is kind of a reference, very much like acetic acid, where you're looking at basically the pKa of a primary amine without influence of additional atoms nearby that may influence electronegative effects. You will see that the pKa for an amino group in methylamine is about 10.6. So you have a minor depression from 10.6 to 9.6 for that alpha amino group in glycine. This effect is due largely to the electron withdrawal by the electronegative oxygen atoms in your carboxyl groups, which increases the tendency of the amino group to give up a proton. Hence, the alpha amino group has a pKa that is lower than that of the aliphatic amine, methylamine. So one of the takeaways here that you should take note of now is that the pKa of any functional group is greatly impacted by its chemical environment. And as you'll see later, this is a phenomenon that is exploited often in active sites of enzymes. You'll find carboxylic acids or primary amines that undergo what is called pKa tuning, such that the pKa's are shifted one way or another towards the direction of favored catalytic function by the enzyme. So in the event that, say, I need a deprotonated carboxylic acid, I need the carboxylate, perhaps I put in the active site nearby that carboxylic acid positively charged groups that maybe stabilize the carboxylate form. The point here is that when you look at the table of pKa values that I showed you in the last lecture, what I want you to see there is that those are under ideal conditions. Those are actually for the pKa's correspond to those functional groups free in solution in the given contexts. However, the pKa's themselves are subject to change based on the local chemical environment. Now we're going to pivot back to the idea of isoelectric point. We're going to work out a couple of examples using amino acids that do have ionizable R groups. So in these cases, we have three ionizable groups. We have our alpha carboxylic acid, alpha amino group, and our R group. And so the first example that we're going to look at here is glutamate. So here I'm showing you the structure of glutamate in its fully protonated form. You have your alpha carboxylic acid here, alpha amino group, your alpha carbon, and then your R group, so two methylene groups and a carboxylic acid down here. Now, here we have to sort of take stock of pKa differences. I would recommend that you look back at the general pKa's for your alpha carboxylic acid versus the side chains of aspartic acid and glutamic acid, you'll find that the alpha carboxylic acid has a lower pKa of about 2 relative to the pKa of the side chains for aspartic acid or glutamic acid, where those R groups have pKa's of 3 to 4. You'll find that aspartic acid has a pKa of about 3.2, and glutamic acid has a pKa that is about 4.25. Okay, so we have our fully protonated form here, and if you look at this, you'll find that the overall charge is +1. We have 3 ionizable groups where 2 of them, when protonated, have a neutral charge. The carboxylic acid here and here, when protonated, are neutral in charge. The only charge here in the protonated state comes from that alpha amino group. Okay, so looking at the titration curve, pH on the y-axis, concentration of hydroxide on the x-axis. Down here, very low pH, no hydroxide, very low pH. We are going to assume that we are starting with the fully protonated state. Then we start titrating in some sodium hydroxide or some potassium hydroxide, some strong base. And we start increasing the pH. Okay, so what we're going to find is an inflection point that corresponds to the first pKa. And this is where you need to try to remember the general pKa's, because here the alpha carboxylic acid versus the carboxylic acid R groups found in aspartic acid and glutamic acid, if you don't know that they are in fact different, you're going to have problems here. So you need to remember that the alpha carboxylic acid is going to be the first to protonate in this flow. So if we start down at pH 0, as soon as we hit about pH 2, the alpha carboxylic acid of glutamate, and really any amino acid, but glutamate and aspartic acid, are going to start deprotonating. So when we hit that pKa, remember at the pKa you have 50% acid, 50% conjugate base. So here our conjugate base is this glutamic acid structure, just now minus a proton on the alpha carboxylic acid. So that is what is happening at pH equals 2.19. Now remember, at this condition, at this first pKa, we have 50% fully protonated glutamic acid and 50% of the singly deprotonated glutamic acid. So here we have 50% this, 50% that. If you remember the charge conversation that we had, the fully protonated form has a net charge of 1, and now the singly deprotonated, the conjugate base here, has a net charge of 0. This is our electrically neutral species. So when my pH equals 2.19, when I'm at this first pKa, the overall charge, the overall electrical charge of my solution is 0.5. I have 50% of a +1 species, 50% of a neutral species. The average is 0.5. Okay, so now I'm going to keep on increasing the pH. You'll see here's my PI, but I'll come back to that. I keep on increasing the pH to my next pKa. So if you remember, the next pKa, if you want to order the pKa's out, and that's a wise way to go about a problem like this, draw your fully protonated structure and then write out your pKa's from smallest to largest. The next largest pKa corresponds to the side chain of glutamic acid, the R group here. It is going to be 4.25. So when my pH hits 4.25, when my pH hits 4.25, I have 50% of this and 50% of that. So my carboxylic acid group, I have 50% protonated or 50% acid, and then 50% conjugate base or deprotonated in this case. So when my pH equals 4.25, I have a net overall electrical charge of minus 0.5. The average of 0 and minus 1 is minus 0.5. Now if I keep on increasing the pH to the final pKa that corresponds to my alpha amino group, I'll see that at a pH of 9.67, I have 50% protonated primary amine, 50% deprotonated. So when pH equals 9.67, my overall electrical charge for my solution is minus 1.5, the average of minus 1 and minus 2. Now, the thing about calculating your isoelectric point is that, if you recall, it is going to always be the average of 2 pKa's. Now, previously, for examples like glycine, it was easy enough to figure out that, because you only had two functional groups that were ionizable. Now you have 3. So remember, the pH that equals my Pi is going to be the condition that favors my neutral species, my electrically neutral species. So what you should be interested in, if you draw out fully protonated form and walk it all the way down to fully deprotonated, what you should be interested in are the pKa's that lead to and lead away from my neutral species. So if I have 3 functional groups that are ionizable, I only care about 2 of them. And that is going to be the 2 that flank on either side my neutral species. Because if you remember, the average of these 2 pKa's is going to be the condition that maximizes the population of neutral molecule. Remember, when my pH equals this pKa, my charge is positive 0.5. When my pH equals this pKa, my charge is minus 0.5. So at the Pi, which is the average, the midpoint between these 2 pKa's, I have maximally populated my neutral species. So here, the Pi is calculated as the average of 2.19, or pK1, and 4.25, or pKr here, my side chain pKa. And the average of those 2 pKa's is 3.22, which gives me my isoelectric point. Okay, so now we're going to work out the problem of histidine. And one of the reasons I'm doing this is I want you to understand that these problems, these isoelectric point problems, are you should be treating them on a case-by-case basis. There are not universal rules that say, oh yeah, if your R group is charged in this way, you need to average these pKa's. It really saves you time and helps you to really understand what's going on if you just work out the problem as we are going, as I'm showing you. So the first step here would just be to write out the fully protonated structure of histidine. So if you do that, you'll see you have a positively charged alpha amino group. You have your neutral carboxylic acid in the form of the alpha carboxylic acid. And your side chain imidazole has a +1 charge when protonated. So the overall charge for this fully protonated form is +2. Okay, so now we're going to turn back to the titration that we've been doing. This type of representation where we plot pH as a function of hydroxide concentration. So before I actually go into this, again, this is a point where it really would help you to have the pKa values handy. So then you know the order of events as you increase the pH. You know which groups are going to deprotonate first, which one comes next, and who comes last. Here you have 3 functional groups again, so just knowing the order of events is very helpful. So as always, our alpha carboxylic acid group has the lowest pKa. It's going to be about 2. In fact, you'll see here it's 1.82. The next group that is going to deprotonate based on pKa value is the side chain, the imidazole. It has a pKa of 6. The alpha amino group is going to deprotonate last at the highest pH. It has a pKa of 9.17. So as you do this, knowing the pKa's is really helpful because you can then order them out and you can really predict the order of events. Okay, so again, we have a plot of pH as a function of hydroxide concentration. So I'm going to start with a fully protonated histidine molecule, and then I'm going to start titrating in hydroxide such that we raise the pH. So based on knowledge of the pKa, when I hit a value of around 2, in fact, when I hit 1.82, I have my first inflection point. So this is the first midpoint that we are concerned with. And this is the pKa that corresponds to the alpha carboxylic acid. Here you have a population that is 50% fully protonated, 50% acid, and then 50% conjugate base, where the only difference here is the protonation state of our alpha carboxylic acid. Now in this example, when my pH equals 1.82, I have 50% this, 50% that. So if the fully protonated species has a net charge of +2 and the next protonation state has a charge overall of +1, when my pH equals 1.82, the overall net electrical charge of my solution is going to be 1.5, the average of 2 and 1. Okay, so now I'm going to keep on increasing my pH by introducing increasing amounts of hydroxide. I'm going to hit my next pKa, my next inflection point. So here, my pH equals 6. This is the pKa that describes the imidazole side chain. Okay, so when pH equals 6, I have 50% of my +1 species and 50% of my neutral species. Here, remember, I'm losing this proton right here. So losing that proton takes me from an overall +1 charge to an overall 0 charge, where the charge in the 0 species is canceled out between the alpha amino group and the alpha carboxylic acid groups. Okay, so when pH equals 6, 50% this, 50% that. If you calculate the overall charge, it's going to be positive 0.5. The average of 1 and 0 is 0.5. Okay, you can sort of see where we're going here. Remember, when we're interested in the isoelectric point, we're interested in finding the condition that populates the neutral species. We just found the pKa that leads to it, and the next pKa, the only pKa remaining, is the one that leads away from it. So now, if we hop up to the next pKa, 9.17, this corresponds to the alpha amino group. So if we increase the pH to 9.17, I have 50% of my neutral species, 50% of the -1 species. So the overall charge here is going to be minus 0.5. Now I can easily calculate the PI, the isoelectric point at this stage, because I know the pKa of the events that lead to the neutral species and away from it. So the average of my pKr, my side chain pKa, and my pKa for my alpha amino group, the average of 6 and 9.17, gives me a value of 7.59. So 7.59 is our isoelectric point here. One additional thing to take note of here for histidine, or really any of the amino acids that have ionizable side chains, is that they also potentially function as effective buffers. If you think back to chapter 1, we talked about what makes a good buffer. And the ultimate definition was something that has a pH, or rather a pKa, near the pH that you are interested in working at. And the logic there was your buffer having a pKa nearby that pH allows for you to very effectively resist changes in pH of a solution when you add acid or base to it. Remember, that was the definition of a buffer, something that allows for a solution to resist changes in pH when challenged with additional acid or base. Now, if you look at histidine, for example, you'll see because we have 3 pKa's, we effectively have 3 functional buffering regions. So histidine could be functional as a buffer from pH's 0.82 up to 2.82. Remember, a buffer is typically effective within a pH range that is plus or minus 1 pH unit off of your pKa. So based on your pK1, 0.82 up to 2.82. Or 5 to 7, because I have another pKa at, for my side chain. So 6 plus or minus 1 pH unit. Or 9.17 plus or minus 1 pH unit. So here for histidine you have 3 effective buffering regions, and in fact histidine, glycine, many amino acids are actually used as buffers both in the lab and in cells. So the amino acids, because of their acid-base properties, are effective buffers in addition to the other acid-base chemistries that they do. Okay, before we conclude, I'm going to work out another problem here. I thought I would work out the example of arginine and maybe one additional problem before I conclude, just to give you more practice in seeing how to calculate isoelectric point. So I've gone ahead and drawn the structure of arginine here. I want to make a note, this is my alpha carbon right there. I have my alpha carboxylic acid here, my alpha amino group here, and this is my side chain. Here I have the guanidinium group, 3 methylenes connecting the guanidinium group to my alpha carbon. Okay, so before I move on, one thing you might be wondering is, oh no, he told me to work out these problems by drawing the ionization states, all of the ionization states, which means I have to draw this structure how many times? Okay, that is kind of a pain. So what I usually do is, for something like this, I am going to draw out the alpha carboxylic acid, alpha carbon, my alpha amino group, but then I'm just going to draw my R group like this. I'm just going to draw literally an R. And if I know the structure of arginine, I know that this is going to have a +1 charge, so I'll just draw that. And for my purposes, that tends to work, especially for a problem like this. It does help that you can draw the structure to start with, so if you do something like this, that's great. Now if I do this, I'm going to start by drawing it like this, and let me calculate the charge. So this 1 and 2 has a +2 charge. Okay, so now let me just go ahead and draw out the ionization states. Now, very, very handy thing for you to have in front of you when doing this. It's your textbook. And I know this is kind of blurry, but this is that big giant table that you all hopefully recognized. Now, when I do this, and I guess I'll go ahead and draw out the pKa's here. My pKa for my carboxylic acid, if I look at that table, is 2.17. So 2.17 for my carboxylic acid group. Hopefully you can read that. My next pKa, which is for my alpha amino group, is 9.04. 9.04 for NH3 group. My last pKa for my R group is 12.48. So you write that as R group. Okay, I apologize. My handwriting sometimes does look like chicken scratch, but I've tried my best to give you in a semi-organized way what you need here. So I have my 3 pKa's. I have my fully protonated structure. I know that if I order these, 2.17 comes before, 9.04 comes before 12.48. I also know which functional groups correspond to each of these pKa's. So I draw the fully protonated form, and I assume I'm at pH 0. So I increase the pH a little bit, and now I'm going to reach my first acid-base event, my first deprotonation event. So that is going to involve this proton. I'm going to lose the proton on my carboxylic acid to give the carboxylate. Okay, now I have a +1 charge. So -1, +1, +1, overall, +1. Okay, so I'm almost there. But one thing I can already say, because now I have my +1, the next is going to be my 0 state, is that the pKa for my carboxylic acid is not going to be used to calculate my isoelectric point. Okay, so now this was supposed to be a bidirectional error. I don't know why none of you caught me on that. Okay, so bidirectional, that's an equilibrium process. My next step is going to involve the deprotonation of the primary amine here. So Q, C, H, now this is going to be NH2 and my R group. So my charge on this is now 0. Okay, so here I'm just going to go ahead and write out the pKa right here that led to this. So from here to here, the pKa was 9.04. So when pH equals 9.04, I have an overall 0.5 charge, 50% of this, 50% of that. So the average electrical charge, 0.5. Cool. Because I've run out of room on this page, I'm just going to try to fit this in as best as I can right here. So now the last deprotonation is going to be for the guanidinium group on the side chain. So C, okay, now my R group is neutral and I have a -1 charge. And this occurred with a pKa of 12.48. So when the pH equals 12.48, overall I have a net electrical charge for my solution of minus 0.5. 50% of this, 50% of that. Okay, so now I know which pKa's I need to use to calculate the PI, and I can do that. So if I write out my PI, it's going to be 9.04 plus 12.48 over 2. If I do that, I get 10.76. So that's my answer. My pH that gives me maximum amount of 0 charged neutral arginine is 10.76. My PI is 10.76. Now hopefully you're following along, because now that I'm looking at this piece of paper, this is chaos if you don't know where I started and the flow. But for that reason, I'm going to go ahead and work out a second problem too. I'm going to pick another amino acid that has an ionizable side chain, so we can try another example. Okay, the example I'm going to work out for you now is that of tyrosine. So I have tyrosine drawn out here for you, and I actually wrote the symbol Y just to really reinforce some of the one-letter language usage. Before I go any further, I'm just going to go ahead and label my pKa's for you. So the alpha carboxylic acid group here, I have the book just to the left outside of the screen here, so you can't see that I'm looking at the book over here, which is what you should be doing too, just to really work, to hammer in these concepts. So the pKa here is 2.20. The alpha amino group has a pKa of 9.11. And this phenolic proton here also has a pKa of 10.07. Okay, so again, I don't want to draw this every time. So what am I going to do? I'm going to go ahead and just abbreviate this when I start working this problem. First, this is the fully protonated form, so I'm just going to draw my abbreviated version of this. And my R group here is neutral. Yeah, okay, neutral. So my overall charge here is +1. Cool. I'm already at the +1. Okay, so the first thing that's going to happen is going to depend upon the functional group with the lowest pKa. That's 2.2.
So the order of events here is going to be alpha carboxylic acid is going to deprotonate first because it has the lowest pKa, then my alpha amino group because it has the next highest pKa, and then my phenolic proton because it has the highest pKa of the three. So 2.2 is what comes first. So I write that out. My carboxylic acid becomes a carboxylate. Okay, now I have a neutral species. My overall charge is 0. Okay, so I'm going to take it to the next step. Deprotonate again. That's going to be the alpha amino group over here. So my primary amine becomes, my NH3 becomes an NH2. Carboxylate, C, H2, N, R0. Okay, now my overall charge is -1. -1, 0, 0, -1. And the pH that gave me that was 9.11. Okay, so you can keep on going. If you were to deprotonate the phenolic proton, that would give you a terminal ionization state of with charge of -2. If I take the proton there, this R group becomes negatively charged. So overall, we could reach a -2 charge. But we're interested in the events that lead to the neutral state and away from the neutral state. Because if you remember, the average of the pKa's that lead to and lead away from give me the mean that a mean value that corresponds to the pH where this thing, this neutral species, is maximally populated. So now that I have these three ionization states, I can already go ahead and calculate my pi, my isoelectric point. So the pi here is equal to 2.2 plus 9.11 over 2. Let's see what that comes out to. 2.2, 9.11 divided by 2. So my value here is 5.66. Okay, so while I'm on this topic, what I want you to go ahead and start thinking about is, earlier I told you you can use the PI to make predictions about the net charge of an amino acid under physiologic conditions, or really under any condition. So when my pH is below, for tyrosine, when my pH is below 5.66, the overall net charge of the amino acid free in solution is going to be positive, because if I favor my net charge of 0 at pH equals 5.66, any pH below that gives me a positive overall electrical charge. When my pH is above my pi, a similar story, except now the overall net electrical charge is going to be negative. Now, one thing I want to go ahead and point out is that when you see, say, tyrosine in the context of a protein, in a polypeptide chain, you have condensed the alpha carboxylic acid group and the alpha amino group with adjacent amino acids to form adjacent peptide bonds. Therefore, you remove the ionization properties of these, and you only are dependent then on the ionization properties of your R group. So if you see a tyrosine that is incorporated into a protein or polypeptide chain, and the pH is above 5.66, really that doesn't mean a whole lot, because the PI doesn't really, as we've calculated it here, it doesn't apply in the same way there. Once we move into the next section, I'll start showing you how to calculate PI values for polypeptides. And you'll see that the rationale is largely the same, but the interpretations have to be a little bit different. So be careful about how you interpret the PI. Is it for an an amino acid, or is it for a full polypeptide chain? Just be thinking about these ideas. But generally speaking, the rule still holds that when your pH is below your pI, your molecule is going to be positively charged overall, and when your pH is above your pI, you're going to have an overall negative charge. So just try to keep that in mind. Okay, so this concludes our discussion of the isolated amino acids. We are next going to move into discussion of the different layers of structure for proteins. But that conversation requires knowledge of the amino acids and the functional groups that are found within the amino acids. So this material that we've been talking about with regards to the free amino acids, it is going to be the foundation for what is to come later. So just try to go ahead and, as much as you can, go ahead and learn your functional groups, learn the amino acid structures, really start practicing the calculations of isoelectric point. Start thinking about the Henderson-Hasselbalch equation, because you'll see some of these things will come back later as we build into protein structure and function. A lot of the material in this class builds upon previous material, so you really need to try to stay up on all of your material, especially when we start talking about applications, because a lot of the questions that you're going to see on exams are going to be application centered. For example, here's an amino acid. Tell me the isoelectric point. Okay, that's one part of your problem. Now tell me, what is the charge in solution? What's the charge going to be at this pH? So things like that. So be thinking about how you would apply the material. Now, I've tried to work out additional problems for you here, but I do encourage you to just go to your book and work out as many problems as you can. In fact, if you look, you have 20 amino acids that you can choose as practice problems to calculate isoelectric point. So do that. Go work out the problems. So lastly, I'm going to try going forward to structure these lecture videos to sort of give you an idea of where we are going next, and that's what I'm doing now. Hopefully you can forgive the varied location. I'm recording these coming off of the spring 2020 COVID-19 pandemic, and so I'm having to do some recording from home, some work from home, doing some in my office, hence the plant that is freshly dead behind my head. So it wasn't watered a whole lot while I was working from home. Hopefully you can let that one go. But this is sort of going to be the structure going forward. So just sort of be on the lookout for these regular repeating patterns.